Welcome.
Take that question.
So today we're going to do Gaussian processes. Hands up if in your heart of hearts, if you're going to be one of the 10,000 people today. So this is the XKCD thing where like every day 10,000 people learn about some new thing in some regard. And sometimes it's something that you know, but you didn't quite know. Who's going to be part of the 10,000 today? Yeah. Okay, the rest of you already know this and here to judge. That's also okay.
Heckle. We're here to heckle, not judge.
That's good. That's good. And so feel free to interrupt. Feel free to interrupt as we go if there's something about understanding. But if there's a question that is like can wait until a little bit later, feel free to like the right point to interrupt me a bit later. Okay. So Gaussian processes, I think, are a little bit confusing when people first hear about them, in part because they get explained in lots of different ways. And each one of them is a little bit confusing. And you might hear one thing, and then somebody explains Gaussian processes to you in a different way, and you go, wait a minute, I thought it was this other thing. And the thing is that actually all of them are true, right? So there's many ways the Gaussian processes sort of sit at the intersection between a lot of things that we think about in data analysis. So one way is that I like to think about it to start off with is that we're used to modeling data by changing like a mean function, by like putting parameters into some function that would be like the mean of all of our data. And that's what we're typically used to. But when we work in Gaussian processes, we're modeling data in covariance matrices, not in data, which is a big difference to what people are used to. Another way you could think about that is that actually you've got like some huge number of data points, like n data points, and we're going to assume that all of them are drawn from one very, very big Gaussian distribution, right? So they're all drawn from one big Gaussian distribution, and data points are correlated with each other. These two things are basically the same.
By big, you mean multidimensional?
Yes, but good. By big, I mean multidimensional, and by multidimensional, I mean if you have n data points, then n is the dimensionality of your Gaussian. Oh, Will, oh no, we need someone to
use that same.
I think it's actually out there.
Oh, okay.
2 to 3.
Okay. We don't want to mutate. Okay, so in previous lectures, we talked about when you're modeling data and each data point is independent from each other. That is no longer the case either. Now your data points are correlated with each other. So that's like an assumption that we're going to break, and the end result of that is that we're going to use
do the pot for you back there.
Yeah. And we're also, Gaussian processes are also the representation, like the limiting case when we have a linear model.
Right. Yes.
Okay. When we have, I wasn't sure if it was just in my head. It frequently is, and I have to check whether other people react. But when somebody else reacts, I think, it's also in your head. That's good. They're also the limiting case. So if you have a linear model, right? Linear model that we're all very familiar with. When you have a linear model, when you have the number of features in your model go to infinity, that is also a Gaussian process. Right? So all of these things are true. And the last point of this is that they represent the infinite set of functions that are consistent with data. Now, infinite has both got quotations around it and it's an underscore because two infinities are not the same. Like there's an infinite infinite set of numbers between 0 and 1, and an infinite set of numbers between 1 and 2, but there's more infinite numbers between 1 and 2, 0 and 2 than there are, whatever. So we're going to come back to that when we speak about kernel functions. And so for all of these reasons, Gaussian processes end up being very popular, both in the physical sciences and in machine learning. Partly because they're rigorous in principle, that's why the physical sciences people like it. They're extremely flexible, which is why they're very popular in ML. And they represent like a very nice non-parametric function. So non-parametric, if you haven't heard of it before, that seems like there's no parameters, but it's actually the opposite. It means you've got many parameters. So, but sometimes that's exactly what you want. And the other important thing is it gives you very nice uncertainty quantification. So often we care about modeling something, not just because we care about the parameters, but we also care about making predictions, and we care about having good uncertainties on those predictions, which is why Gaussian processes come up a lot in a lot of different situations. Okay, any questions on that? Yeah, good.
Yeah, I didn't understand. What did you mean by features of the linear models?
Right. So if you have a linear model like of y equals ax, where a is some big design matrix, and that could include like a column vector of ones to represent like a bias term. It could encode like a column of x's and x squared or x cubed or whatever. You can increase that design matrix to be as big as you want. And if you increased it to infinity, as in you include every possible thing, which we're going to do in a second, that represents the case of when your linear model is going to infinity. It has m features that go to, m is infinity. And when you get to m of infinity, you get a Gaussian process. So Gaussian process is technically like a linear system, even though they can model nonlinear data. Any other questions before we start? Okay, good. So normally we're in a situation like this, where we have something like time and we have some data. And the example I'll give here is one that's common in astronomy because it's a great situation where it's some very precise measurement. It's dominated by systematics, right? So the situation here is that there's a little bump here, and the bump is caused by a star, a beautiful star. It's got a little planet that goes in front of it. So the star temporarily gets fainter, right? Now, this difference here that we're talking about is of order like 10 to the minus 6. So it's extremely small, and so you have to be able to measure this to 10 to the minus 6 over a long period of time and do this many, many, many times. Now, if all of your individual data points are independent of each other, this is easy. You don't have to be here, right? It's done. But the problem is it doesn't look like this. What happens is these data were actually taken from a telescope in space, and that telescope in space is affected by lots of different things, right? It's a very complicated thing. And what you actually see is something that's like this. Right? And then here, I'm going to draw a tiny little dip. And this difference, this might be 10 to the minus 1, right? Something huge, dominates the signal. Now, the problem is, if we knew everything about the telescope, if we knew everything about the telescope entirely, we would be able to predict like what this pattern is and what causes it, right? But it's caused by lots of different things. It's caused by like the temperature of the telescope at any one point in time, the detector sensitivity, which could have some very complicated function. There's clearly some periodicity here, so maybe there's like a pointing issue or a drift issue. It could account for like how many meteorites hit the telescope in the last 10 minutes. It could matter based on the number of pieces of toast your friend had for breakfast. Now, that seems insane, but how could that be? Well, it turns out your friend works at the Space Telescope, and their job is to make sure they turn on the cooling system at the right time, and for some reason that's not a cron job, and if they don't have a breakfast that morning, they forget, and therefore there's a change in the telescope, right? That seems crazy, but the thing is, we can't write this down. We have no idea what causes this. All we know is that it dominates our signal, and that there's any number of things that could be causing this signal. Okay, so the other way to say this is that these points actually are correlated with each other. So it's not just about what was causing the measurements at a given time, but actually like here and here, whatever it is that's causing this signal, these 2 points are correlated with each other because they were taken soon after each other. That's the whole point, right? So it's a very complicated thing that we can't write down, but what we can write down is that they're correlated on short time scales, but also on long time scales, right? There's periodicity here. So what we're going to do instead is we're going to try to model what everything could be to account for this signal. So, and what we're going to end up with is a Gaussian process. So normally we'd say something like this, right? That our data are distributed with some mean function and some covariance function. It would be like that. It's no longer going to be like that because, we're doing things that are difficult. And so instead, we're going to introduce something to account for all of these possible systematics. And the point of all of this is that we're going to go through the math so you can see where Gaussian processes come from. I will skip one step and I'll tell you where I'll skip that step, and you can do it at home if you want. And then after that, we're going to go into speaking about like how you do things in practice with Gaussian processes. So we'll go through the math first, which is often described as the weight space view. And it's all it is that where we start with a linear model and we're going to end up with a Gaussian process. That's it. So we're going to use a linear model first to model all of these systematics that we don't know what they are. So instead of being in this situation, we're going to rewrite it like this. Right, we're with A and W. So A here is going to be some very big design matrix. where there could be ones along the first thing, could be temperature at the spacecraft at some time, right, down to T of n. It could be the temperature squared. It could be the temperature cubed. We could include all of these things because we don't actually know what is causing the issue. So if we don't know what's causing the issue, we should just include everything. So this is number of pieces of toast that Sam had for breakfast at some given day, and everything else that we can possibly think of. Now you can imagine as we're going along this direction, m is going to go to infinity, right? We're going to include everything we possibly can, absolutely everything we can about this system. And the weights are going to be like how much this thing contributes to the overall signal. This is going to be weight of m, so m features, okay? So we've got our mean model, which is the transit that some of us might care about. A is this big design matrix, which includes everything we can possibly know at any one time. W is some set of weights that we don't know what they are. And C is the covariance matrix of the data, okay? All right, now the whole point of what we're going to do here is we're going to move this into something here. That's the point. When we get to what that is, we're going to talk about what it is and then how you use it in practice. But that is the goal here, okay? So if you're going to fall asleep for a few minutes, this is where you should wake up. And I'll let you know when you should wake up. Okay, so we can start out with the log probability for this. AWs already. Okay. And everything you see here is going to be natural logs. I don't like the ln terminology. I'm going to try to write ln and not say it, but you know, if you want to contribute and I say log, you can ask, do you mean natural log? And I'll say yes. So, okay, so this is the ln probability of the data when we have this AW thing, okay? Now, this thing could be big, and this is just like how much each thing contributes to the signal, but in reality, like we don't actually care what these weights are, right? We actually care mostly about the mean signal. Everything else is nuisances, what we'd say in data analysis. It's a nuisance to our system, but we need to account for it if we want to measure this thing very precisely. And so I don't actually care whether it matters whether Sam had toast for breakfast or not. I don't actually care whether it matters based on the temperature cubed or temperature squared or whatever. I don't care. I just want to account for it. And when you're in a situation like this and you're Bayesian, well, the way that you can do this is by introducing these parameters and then marginalizing over them. So to recall, like what marginalizing means is that we're going to consider every possible value of what WO could ever be from -infinity to +infinity, and we're going to integrate out all those probabilities, so it doesn't matter what this value is at all, right? We'll integrate it out. And because we're Bayesians, we can do that, but there's something that we need in order to be able to do that. So what we need is a prior on W, right? So the probability of Y given the model parameters theta is equal to the integral from -infinity to +infinity of the probability of Y given the model parameters and the weights multiplied by our prior probability about the weights, integrated out all of those, okay? This just comes up a lot. This is just like marginalized conditional probability, okay? So in order to do this though, we need this prior on the weights. And I just told you, like, we don't care about them, we don't want them, and we don't know what they are. That's kind of the point of all of this, right? So we might want to say something like, well, I don't actually know what they are, and so I'm just going to say they're uniform from -infinity to +infinity, and you're going to say, ah, I'm so clever, look at that. Why can't you do that,
Not normalizable.
It's not normalizable. It's an improper prior, right? It doesn't have a finite integral, and we need a finite integral, right? But an alternative is that you could introduce some very, very large Gaussian or something like that instead, which has support from minus infinity to positive infinity, and we don't actually have to specify what that really is. So let's just like make up some shit where the stuff we make up is going to be the weights have some prior, it's a normal distribution centered on 0 with some covariance matrix lambda. Now, at this point, you might be thinking, we are just making stuff up. There's no point here, right? That's true, but the point is that we're going to go from this to that, and this is how we're going to do it, okay? It's just this and a little bit of math. So let's do the little bit of math. My son. Okay, so the non-prior of the weights is equal to minus a half W transpose lambda inverse W minus a half lambda 2 pi lambda. Okay, and so we know what this probability, like the log prior probability looks like. Well, we know what the prior probability looks like. We know what this looks like. We wrote it out here. So we can actually just combine these two together and then see what happens. It's just going to be moving stuff around after that, okay? So if we want so we want this integral. So here we want multiplied by 1 over. I'm not going to have space. Okay, so dw. Okay, this is our integral, right? All we've done, we've got this, we've fed in this, and we fed in this. We still actually have to do this integral. And actually it turns out that this gets a little bit, it looks a little bit nasty. So we'll just like group some things together first. This is a Z or a Z, depending on your religion. R is just the residual now, so it's going to be that, just for characters. Okay, so this actually like kind of sucks, actually, but there's at least 2 reasons why everybody uses Gaussians. One of them is that the universe tends to produce them, like you have a bunch of true-false statements and you end up with a Gaussian, you're like, how did that work? The other reason is that Gaussians are actually magical. And Tom Hilner has heard me say this about 1 billion times before, because they really are. And one of the things that's magical about them is that a convolution of a Gaussian, oh, I've removed the goal. Okay, because the convolution of a Gaussian with a Gaussian is a Gaussian. And that might not seem very important to you, but it's like really, really handy because Gaussians have analytic integrals. And so if you have Gaussians and you have other Gaussians, you smush those Gaussians together and make them kiss, you end up with another Gaussian that you can integrate analytically. And that's also good, and they get to kiss, so that's good. And so this is the point, is this the point where we'll do it? Yeah. So this is a Gaussian, right? This is a Gaussian, this is a Gaussian. You might just have to trust me for a second. We're not skipping the step yet, but you might just have to trust me for a second that the convolution of a Gaussian with a Gaussian is a Gaussian. And so we know it's going to be a Gaussian. So we could say that actually like that thing would be way easier to integrate if we had it in this form. If we had it in this form, right, that we're all familiar with, where K didn't depend on W at all, then we can integrate this and we're done. That's good. That's what we want. Now, this is the part where we're going to skip a step. Okay? It can be shown. And what by that I mean, all you need to do is to take this and expand out all the terms and collect them back together. It takes about 3 or 4 pages of linear algebra, and like 9 out of 10 times I've ever done it, I've missed a sign somewhere and messed up something at the end, and you don't find out till the very end, which is like really satisfying. So if you have like a 3-hour meeting or something like that, and 75 napkins, labor bobs, it can be shown that here, that big sigma inverse is equal to lambda inverse plus A transpose C inverse A. That's good. And H is big sigma A transpose C inverse R, and K R transpose C inverse minus C inverse. We're going to change K later, but this is what it comes out as initially. We're going to change it as in we'll use an identity. It's exactly the same function. But it can be shown that we can write this using these, and we will get exactly the same thing as over here. Except now we have it in a nice form where K doesn't depend on W, so we can actually do this integral analytically. Right? We can actually do the whole thing analytically. I'll write it out. Well, actually, it's this one. Here it is. Yeah. Except we missed an integral there. Where at the end, you get something that's lovely. So we'll do it here. A does not depend on W, that's why it's on the outside. So we've got then the exponent of the thing that we want. W. All this we see that. Yeah, we can. Okay, so this integral is now our favorite distribution with its analytic integral. So we have all of this, right? Now I know you're thinking like this is a lot to just get to like this and this, but we're about to be there. And actually, like this is where the fun bit comes. So, I mean, presumably you were having fun already. I will not be taking a survey on that, but like, I'm just going to assume that it's true. But it's so lovely because this is like, everything just comes from a linear model. This whole thing of Gaussian processes, it is magical. That's because Gaussians are magical, but it all just comes from a linear model, okay? So now we're going to use so this is where I said we skipped a step. Here we're going to use 2 things, the matrix determinant lemma and the Woodbury identity matrix, just to have things in a slightly nicer form. So that's the matrix determinant lemma. And we're going to use Woodbury to rewrite this, which I told you we would do before, into something that's a little bit nicer. B plus A lambda A transpose R. Yes. Okay. So now we can go back to this. And we got there, basically, give or minus 25 minutes. Here we go. Let's write this out now. Something magical has happened. Yes. Is it positive?
Yeah.
Yeah.
Not about you, actually.
Well, then I don't want to hear it. No, go on, sorry.
Yeah, so this trick that Andy is showing is very well written in data analysis recipes by colleague Adrian.
Yes,
And
it
I
is.
call it Adrian's trick.
They call it what?
I call it Adrian's trick.
The kernel trick? You call the kernel? Oh, wait.
The multiplication of Gaussian.
Trick. It's not.
Oh, right, yeah. Well, it is Adrian's trick. It's the Price Whalen trick, actually.
Yeah.
I can't believe we did so much science before we could multiply Gaussians together. But that shows how good Adrian is that he was able to do that much science without multiplying Gaussians together.
No, but I really recommend that read.
Yes, yes. In fact, so there's Google Doc with notes for this, for like this set of classes. What is it D?
I don't know.
Some combination. There's a full stop in one of these. Maybe it's that, and it's like data CCA, where there's some resources that I've put in there. Hog sent it out in his email too, but should add anything else to that because there's so much good stuff on the internet about Gaussian processes. And we're going to do one at the end as well. So you should add anything that you find there because there are some real gems. Okay, so we're there. Look at this, right? Another way we could write this just like as you were speaking.
Oh.
Another way we could write this is that y is drawn from a Gaussian distribution with some mean function and a covariance matrix of C, which is your data, plus A lambda A transpose. We did it. Mission accomplished. See ya. Okay, so what have we done? We accomplished this goal in that we moved this thing to something else over here, but we haven't done anything useful yet because like we introduced weights and then we got rid of the weights and replaced them with this lambda, and then now we still have like other problems because we don't know what lambda is, and we still have this A matrix, right? And it appears twice. The question? Yes.
I'm not sure if you said this explicitly, but
yes.
Is C assumed to be diagonal? Like
No.
No.
Oh yeah. So I mean, you can make some things really, really fast if you've got diagonal matrices, but it doesn't have to be. Okay. But the important thing, I think, like the somewhat counterintuitive thing to many people, is that actually, now that we've wrapped things together like this, we have moved our model from, like we have a mean model, but this could be 0, and it often is 0. But we've moved things over to here such that we are now modeling things in covariance space. And this is an n by n matrix. And so this is an n by n matrix. This is our model. This is our data uncertainties. They're interchangeable here. They have, equivalent meaning, which is the total opposite thing. Before you do Gaussian processes, you're only ever focused on the mean function. You're not anymore. And actually, when you model things in covariance space, it's far more flexible with fewer parameters. So anyways, but we're not at fewer parameters yet, because like A is still here. And how big's A? infinity, right? Fine, okay. So unfortunately, even with the computer, the CCA, we can't construct an infinite sized matrix. I've talked to SCC about it to request some more compute. I don't know what the status of that is, but anyways. So we have A lambda A transpose, right? So just to be clear, this has shape N and M, which I'll just call now M, but M is really like infinity. So then, let's just do it. Infinity, lambda is our prior on the weights, and the weights were shape M, and so our prior has to also be shape M. So that's an infinite by infinite size matrix. And then A transpose is an infinite times N. So in the end, with this inner product, you end up with an N by N. Cool, but we had to use every computer on the planet to approximate it. That's not good. This is the trick that I thought you were going to say, which is that actually, when you have infinitely large matrices like this, and they only consist of inner products, you can replace this function. You can replace this with a function K that just depends on one position and another position. And if K has certain properties, you never have to construct this thing, right? So A is now gone. It is not our friend anymore. We're going to use K instead, right? We're going to use K. That's going to be our kernel function. So this is often referred to as the kernel trick. And it is a trick in many ways, but it's like it's so handy that we called it the Price-Whalen trick. And so, and it's applicable anytime you have a set of large matrices that only contain inner products, right? When you've got that, you got this. The other, it relates to something called Mercer's theorem as well, which I could feel some people looking at me saying, you've got to also mention that. So what is it? Like, we're doing things very abstractly. Like, who's lost? Tom, you're at the CCA, you work here. Okay, Tom Wagon's not lost. But do you have a question, Tom?
We'll find out.
Okay. Okay. So let's just rewrite things to be a little bit nicer, and then we'll see what this actually means. Okay. This is the common thing that you may have seen. This is the common thing that you may have seen, where now, yeah, we've just got our mean function. We've got C, if you can read my chicken scratch, we've got C plus this covariance kernel function. So that's nice. Like, we moved some stuff around and now we've got a K, but what are you meant to do with that, right? So the requirements on this being true is that K is a function that can produce a covariance matrix which is positive semi-definite or non-negative semi-definite. So it just has to be basically a valid covariance function. Anything that produces like a valid covariance matrix. Anything that produces a valid covariance matrix can be your kernel. Okay? So that's the only requirement. The question is like, what is it and what do you do with it? Well, there's one that we'll use, there's a bunch of like families that people commonly use. And I'll name some of them and just tell you what one is, because at the end of this, we're going to do a worked example on the board of how you actually predict a value from a Gaussian process. So we're going to invert a matrix on the board. Did anybody bring an abacus for us to work with? Oh, Will Farr, the god at the back of the room with the giant emoji hand. Will, sorry, I don't know how long your virtual hand was raised there. Can you
You saw it in like 50 milliseconds.
Fantastic.
Well done. No, I have a question. So when you're talking about the kernel or the ultimate, the product, A lambda A transpose,
yeah.
That is an expression in data space, right? Like
Yes.
the input and the output
Yes.
dimensions there are data space.
Mhm.
And when we were designing the whole setup, you had a design matrix A that was full of columns of things in, let's call it latent space or whatever,
Yeah.
some other thing. And I feel like when I'm talking about systematics and you make a column that's temperature and temperature squared and temperature cubed and number of slices of toast and so on, I can reason about what's going on.
Mm.
Right? The number of slices of toast is clearly irrelevant, but there's maybe a weak nonlinearity in temperature, so that coefficient should be big, whatever, right?
Yep.
Now we've jumped to this kernel, which is evidently meant to capture all of that reasoning, but has to be expressed as a relationship between two data points with no reference to the latent anything. Can you comment on that? Is that just like, sorry, you got to just live with the crazy? That's what happens? Is there an intuitive way to relate that? Like what? Yeah.
The answer to both of those questions is yes. And I feel like I should have asked you to set up this question because otherwise I was going to skip over that. And it's actually really important. So thank you. That is great. It's totally true, right? Because this had pieces of toast and temperatures and all that other crap in it. And now we've just replaced it with K. Do we even need the pieces of toast? Does it matter? Do we need the temperatures and things like that? And the truth is no, but what we've done is replace one infinity with another. And so here we had an infinite set of things that we were going to include. And that's everything we thought we could possibly have that would affect the data. Now we're replacing it with something else where this can give like infinitely different functions, but two infinites are not the same in that the kernel function you decide on can make some kind of functions, like some kernels can make some functions like this, and some can make things like this, but some kernels are not all the same. Like there are some kernels that are periodic that will always produce periodic signals, but there are some kernels that are only smooth on on relatively short scales, and they will never produce something that's periodic. So if you have something in your data that's periodic, you're going to need to use a kernel that's got some periodicity in it. Otherwise, you're probably going to have a bad time. So what we've done is like replaced some set of choices here about what infinite set of things we should include in the design matrix with which kernels should we use that give the right kind of infinite support that we need. And choosing this, well, is really hard. And there's some like guidelines you can pick, some guidelines to it. But all we've done is like regularization. When somebody says, oh, you could just regularize that, what they're doing is they're replacing they're fixing your problem by giving you a different problem. So what we're doing here is fixing this problem by giving you a different problem. And the problem that we're replacing is you don't need to construct these matrices. You don't need to know how many pieces of toast that were eaten, but you do need to make some decision about the kernel, which is also like setting a prior belief basically on what you think, the kind of data that you could get. Does that address your question, Will?
Yeah, I think so. I mean, I'd love to see a lot of math behind it at some point, but we can sit down and have a coffee for that.
Yeah. Next week at this time. And are there any other questions at the moment? Before we introduce some of these kernels that we're making up, but still. Okay. So a few common kernels. One is called radial basis function. There's a whole Matern family. There's like squared exponential, like what do any of these things mean? Whatever, we'll get to that when we talk about kernel choices. But there's lots, and choosing one of them often is not enough. Often you need to have two where you add them together or you multiply them together, or you need periodic things. Like there's a whole bunch of different things. Yeah.
So in your when you rewrote A lambda A transpose, so A is a function
No, sorry.
depends on your weighted variables that are physical, but we don't know what they are. And K depends on the structure of your data.
The second part of that is true. K depends on the structure of the data. A includes everything we do know, like temperature, pieces of toast, and things like that. W was what included like the latent contributions,
Oh,
basically.
okay.
Yeah, and we integrated W out to replace it with lambda, and then we got rid of lambda because we don't like lambda anymore to replace it with K, and now we're gonna stay with K because K is our best friend forever.
Yeah, because we look at the data and we know roughly how it's.
Yeah, that's kernel. We'll get to kernel choices. Yeah. But yes. So once, and so as I said, they just need to be dependent on data points. So one kernel choice you could have is like a radial basis function or something like that. So you'll do x minus x prime squared over, oops, a negative in here, 2L squared. So here now our kernel function actually itself has got parameters. That kind of sucks. So this is a parameter, this is a parameter, this is a length scale that basically says like how close things they need to be together to be correlated. And this is like basically an amplitude or a variance, like how, if things are really close together, how uncertain or whatever they are. So all of your kernels have got different parameters. And when you hear the term hyperparameter, that's what people mean when it's the parameter in your kernel, right? So these are called kernel hyperparameters. And so it's just a function that you can compute in NumPy or Julia or something like that, that just depends on positions of two data points and depends on your hyperparameters, and it gives you a value back. And so when we're doing something like this, building this n by n thing, we have to evaluate at every single point relative to every other point, except and symmetric, so you save a bit, but it's still expensive to evaluate. Okay. Okay, and you can add kernels together, multiply them, all that sort of stuff. We're just going to use this one for now. And what I'd like to do now is for us to do a worked example on the board, because I feel like most Gaussian process introductions get to here and then they stop and they say, oh, you can choose kernels, and then here's a thing of how you can compute it and something like that. I would like us to do a small GP on the board, and then we're going to turn around to be maximally annoying. And on the projector, we're going to have an interactive visualization of what we've done on the board, and you're going to see like how it works in practice. So this is all going to go, and we're going to do like a homework problem. Any questions while we get set up for that? Okay. So we're going to have some data, and we're going to say it's x, y, and we've got y error. And we're going to say that x, to make things a little bit tractable on the board, how many data points should we include? 100? Is that too many? 50 million? We're going to do 3. So just to show you how it works, as we don't have time. So this is our data, 0.5, yeah, 1.2, and 0.8. And we'll just say all the y errors are very small. We'll just say that they're 0.01. They can be noiseless, and in fact, like many situations, yeah, which is why also GPs are good, but we'll just say that they're very small. Okay, now we want to make predictions at what we call x star. So these are positions that we don't have data for, and we want to make some prediction with our Gaussian process, okay? So what we do is we think about the combination of x and x star as all part of one big Gaussian, right? So if we have, if x star is actually just 3, right? So if we had, say, 1, 2, 3, 4, a 4-dimensional Gaussian, we'll just imagine that they're all part of that big Gaussian, and we're going to make predictions for y star given x, y, x star, and y error. And we're also going to make some predictions on like the, I should call this, well, I'll call it y star, but you might also call it like mu star, like the mean. And we're also going to compute like what is the uncertainty on those on that new point. Okay, so the way that you could write this is that you're going to say that it's drawn from a normal Gaussian. We'll say it's centered on 0. And then our covariance matrix, that was ambitious, but okay. K x dot plus the uncertainties in Y squared and an identity matrix. So that's the top left part of this matrix. That's why it was ambitious. Look, space for that. And then here we're going to have K evaluated at X relative to X star. So at our data points relative to what we want. And then down here, we'll have the symmetry of that, X star transpose. And then down here, we'll have K evaluated at X star, comma, X star. Okay? Now we know how to compute all of these things. This is just evaluating the kernel at the positions that we already have. This is evaluating the positions of the kernel relative to the new data points at star. And so we'll just do a really quick GP, just one quick GP, and then we'll be out of here. So if you want to evaluate this, so you want the mean posterior prediction. So you're going to have X star, X, we'll have K of X dash plus sigma squared Y. Good, yep. Inverse Y. And then I have mu star. This one makes you feel uncomfortable. Well, it makes some of you feel uncomfortable for good reasons, because you're computing a covariance matrix that must be positive semi-definite, and we've started off with something and then subtracting something. So if this thing is bigger than that, you're going to have a really bad time. So a K star, but that's what we're here for, a really bad time. So plus 1, and then K star transpose. Okay, so K X star, so at the locations of the data. So this is going to be K at 0, 0, K at 0, 2, K at 0, 4. Of course, we can just rub them out because that's all going to be 1, because you remember I've removed the thing, but it's like X minus X prime squared 2L squared and a sigma squared at the front. To make things easy, we're going to call this 1 and we're going to call this 1, and I'm not going to hear any complaints about that. So that so this is going to be 1s along here, and then we're going to have here K0, 2. So this is going to end up being something like 0.14. Somebody can check on their abacus whether that's correct or not. Lachlan's nodding, which means he did the calculation in his head. That's good. He's used to exponential, so that's good. And up here we're going to have K04, which if you have an abacus, it comes out to 0.0003. And then we'll have the same on the other side. There's a symmetry, 0.0003. We'll need to do the same thing for K, X, and X star, but thankfully we only have one data point that we have to do this for. So this is K03, K023, and K43, or the other way around. I can't remember. It doesn't matter. These values come out to 0.1, 0.01, 0.61, and 0.61. Okay, we're not actually going to do the inversion on the board because that's an insane thing to do, even for me. But what we'll do is we'll just write out the thing and do what it is, and then I'm going to get the other person who's going to teach you about Gaussian processes for the rest of the day, which is Ryan Rubenzold, because we dressed the same somehow today, and who is also producing like a fast GP, so it seems relevant to get up and do this. So so mu star, right? It's going to be our K star X being here, right? So 0.01, 0.61, 0.61. We have our big matrix now, KXX plus our thing, so that's this, and we're going to add some uncertainties along the diagonal. So those are the data uncertainties, so it's going to be small, like 0.01, 0.01, 1.01, and then 0.14, 0.14, multiplied by our data vector, which I just rubbed out, but 0.5, 1.2, 0.8. That gets us, anybody doing the matrix multiplication? Oh, inverse. Sorry. Don't forget the -1. Inverse gives us 1.03 something. You can do the exact same thing for sigma thing, which we're just going to compute, and it's 0.6, right? So our GP is telling us that if we have these x and y's, so if we have 0 to 4, and we have 0.5, 1.2, 0.8, then at 3, it's going to be about 1.03 with a very large error, actually. And that's because, in part, we set this to 1 and this to 1. Now, we're going to turn around. Oh, but we should plot it. All right, let's plot our expectation. So this is going to be 0, 1, 2. So 2, 1. So here we're at 0.5, at 2, at 4. So at 2, we're at what, 1.2? And then at 4, we're at 0.8. I really picked the wrong scale here, but that's okay. And then what we're saying, our prediction is that at 3, it should be about a little bit over 1 with a pretty large uncertainty, right? Now, the uncertainties on the data are tiny, but if we were to predict the values of this GP and the uncertainty everywhere, what you would see is probably that near the data points, it goes down to 0. So we have some mean function which might look something like this, and you'll have some uncertainties that collapse when you get to the data points. Right? And actually, let's do the annoying thing and turn around and see what it looks like. And I'll bring my thing with you, because what I'm going to show you is like the opposite of the weight space view. And that is, I'm so sorry, I really didn't think how annoying this would be. No, you're okay, you're okay. It is actually me that's doing the annoying thing by forcing the inconvenience on literally every single person.
No, not the sideways people, we're good.
Oh, yeah. Yeah, I told everybody on the sideways, I gave them $20 and told them to sit on the side. Okay, here we go. And then I was told to do preset number 2.
You're good there. I got it already.
Oh, thank you, Jay. Thanks. Then I will share my screen.
Wait, did you? No.
Okay.
Oh, I love that.
Okay, this is linked in the notes. You'll see it. This is one of the great gems on the internet. There are many. Now let's do our own GP. So the GP, the kernel that we've selected here is a squared exponential. That's what we've got. So unfortunately, I did that before Tom reminded me of this. And so if I knew that, I wanted to pick 0 because that's the limit of this thing. So 0, and then at 4, we are at what, 0.8. There might be a way to like put these numbers in, but I'm a bit of a boomer. So 2 and 1.2, right? Okay. Now let's look at 3. The mean prediction at 3 is about 1.03, and the uncertainty is 0.6. You did it on the board, it's right here. This is exactly what it looks like up there. GPs are not that, they're confusing at first, right? But actually doing stuff with them is pretty convenient. So here you can change, you can use this and change data points and kernels and all that sort of stuff and see both the mean predictions and the uncertainty band. All of that you just saw is the weight space view of Gaussian processes. The other view that people like to use is the function space view. And it seems unusual for me to introduce a new view with 7 minutes to go. One of them's hard, one of them's easy. Weight space view is easy, this one's hard. The other way around. The other way to the function space view is that a Gaussian process is a set of infinite functions that is consistent with the data, right? So here you do have some mean function which we computed, but these wibbly wobbly lines, all of those are functions that could be consistent with the data, right? You have many, many functions, infinite set of functions that could be consistent with the data, and the mean of all of those functions is this thing. And the uncertainty in all those functions is this thing. So when you have no data, all you have is basically your kernel, right? Just prior draws from your kernel, and it could be anything. When you give it some data with some uncertainties, you change what it can look like. I think I need to push enter. Now let's bigify it. 1.05 is probably more right. So now the data have uncertainties. You can your uncertainties also grow, right? So the predictions that you make, the mean predictions that you make, depend on all the data that you've got. So sometimes people get a bit confused when they're like, "I've got this GP, I betted all this data, and I get excellent predictions from my data." No, you didn't. Your GP is conditioned on those data. You need to make good predictions elsewhere. And that is kind of one of the difficult things, like when you're deciding about kernels, you're deciding about what you're to do about your parameters. Like here, we just decided to fix them because I wasn't taking questions or comments at this time. But you could optimize them at the same time as your mean parameters. You could marginalize over them if you can afford it, or you could do something like cross-validation, where you sort of predict some part of the held out data and see it with varying different hyperparameters and see what works best. So that's like a consideration for how you like deal with the hyperparameters in your kernel. But as I said, even choosing your kernel is a little bit difficult. If you've got some periodicity, you absolutely need to have some sort of periodic kernel, which you might want to multiply with some other smoothing kernel or something to account for like smooth variations away from that periodicity over long timescales. There's, in general, like unless you have periodicity, and if you don't have periodicity and you don't need a periodic kernel, just try like squared exponential, Matern, 3/2, 5/2, 2/2, like 1/2, and you'll find that one of those does a pretty good job. And if it's not, then actually you're at the good territory where there's lots of people who care about GPs, and they will have very strong opinions as to what you can try and do. So that's like a good state to be in. So just try the few first that are known to you that were on the board. And if they don't work very well, you should speak to other people and see what's happening. One other consideration for when you wouldn't want to use GPs, doing that inverse is a O(n) cubed operation. So if you have n data points, it's n cubed complexity. So that means that if you have 50,000 data points, inverting a 50,000 by 50,000 matrix is going to be, you're going to have like a tough time. So naively it's O cubed, but there are some very good fast methods for doing GPs. And in fact, most or many of them have been produced at the Flatiron Institute, which is kind of amazing. So there are people here who care about GPs. So there'll be notes in the resources, but like TinyGP, Celerate, EFGP, Tom and I are making an F1 GP because we wanted it to be easily searchable. So it's the Gaussian process, the fast one, F1 GP, small GP as well. And their applicability varies in different situations, depending on the dimensionality of your data and what kind of kernels you need. Is there a question?
Yeah. So when the referee asks you, why did you choose this kernel, what do you say?
You say it did a good job on all the tests we made in terms of like cross-validation and things like that, and there's no better choice. So sometimes your problems have a particular characteristic that means you should choose a particular kernel, but if you don't know what it is, then we have no idea. And all you can do is to try, say, more complex kernels that have more parameters and then sample over them. But in fact, like the referee is either, it's actually the same problem when you get a referee who says, why didn't you regularize this? And you can say, well, it replaced with a different problem. We did do that. And this is what we decided on, right? So the thing is, like, you just do the best you can, and it's really informative then to look at the residuals. So look at the structure of your data of when you're doing cross-validation and things, what's not working well and why. That can tell you a lot about what kind of kernel you might need. But in general, broad categories depend on periodicity or not, and how smooth you expect things to be or not. Yeah, but great question. And as I said, infinity is not infinity. So while GP can give you an infinite set of functions, you can see the band here of those different functions. It is not going to give me a value that's predicted at like y of 50, right? That's not allowed with this kernel. So it is an infinite set, but not infinite everywhere. So that's something important to remember with Gaussian processes when you're thinking about infinities and kernels and things like that. Yes.
Andy, when you talk about tests, like, could you just give some examples of standard things? Is it like leaving out a data point and seeing what it gets? Like,
Yes.
what are some of the tests one does?
Yeah, some of the tests would be like that, leaving out whole bunches of data and then predicting on the held out data to see how well it performs. That's like a classic cross-validation thing. You can do that in chunks. So you might say, I'm going to do K chunks. So you're going to chunk out, you're going to assign every data point like a value from 0 up to n, and then you're going to decide on like a bunch of chunks that you're going to leave, and then you do your GP and you predict on the held out data and you see how well you go. And then you could vary your hyperparameters, do it again. That's like a good way to do it because you're sort of like testing against the things that you know. That's kind of the best way. You can marginalize over your hyperparameters, but that still doesn't help you when it comes to kernel choices. So cross-validation is a really great thing to do, because even if you've marginalized over what all the hyperparameters could be, you still might be in a situation where you don't perform very well on cross-validation. So self-consistency tests are really key for GP use. Yeah, great question. Yeah.
Sorry if I missed this, but what happens if your noise is different for each one of your data points? Would you sit in the covariance matrix, or you need to do something different?
Good question. That would go into your covariance matrix. So up there, I just said that they're all the same, like 0.01, but in fact, each data point could be different. And in fact, different data points can be, so you can put all of that into your covariance matrix C.
So you don't need to push that while doing all of this.
That's right. The only point where that ends up mattering is if you're using a particular Gaussian process implementation that is really, really fast. And one of the reasons why it might be fast is because it might have some built-in assumption that all the data points have got approximately the same standard deviation or whatever. And so that we would call homoscedastic. You can always ask and check the docs to see whether that's like a thing or not. Usually the giveaway is that you're not allowed to input an array of uncertainties. It only lets you give in one value. If that's the case, it's because the underlying method is super fast, because it has like some nice linear algebra that is only enabled by having like all the data points have approximately the same standard deviation. Good question as well. Yes, I think this might be the last one because we'll have to stop after this. Yeah.
Thank you. So if you kind of know that your data is plagued by some systematic errors, and you have some like error reading on your data, but you kind of have an intuition of like what sorts of errors is influencing those readings, but you're not sure what. Is that possible to like use the Gaussian processes to discriminate against that?
Fantastic. Not always to discriminate, but actually like what you can do is like a GP is when you don't know all the things that can possibly be causing things, but you can betterize stuff by having like some systematic error model that you put into your mean model, or that you put somewhere else into your covariance matrix. And then the GP is doing all the work on top of that. So any deviations away from the data noise and the systematics that you know about, the GP can capture those. And that's like a really good thing to do, because more and more that you put physical intuition or understanding into either your mean model or your covariance function, the less the GP has to do, and then the more interpretable everything is. So fantastic question. Yeah.